This video will explain some ideas around general purpose reading models in deep learning and AI. To give the motivating headline, I think this paradigm will really help avoid needing massive amounts of parameters in these models and help achieve high performance more economically with less parameters. And I really think this approach has more promise than, say, knowledge distillation from a massive, say, read-only model as you split these kind of models into retrieve and then read kind of pipelines. So to give the TLDR and kind of tell the timeline of the story, we start off with this idea of transfer learning where we have some pre-trained model that's been trained on a very large data set to avoid overfitting. These large data sets usually aren't labeled. They're optimized with self-supervised learning. So you can just do like an internet scrape and get image text pairs, text images straight from the internet, and then you have this massive data set, and then you can just mask out parts of the input and then predict what's been masked out, and then you can scale this up and avoid overfitting. So then what happened, and so from there we were transferring and fine-tuning these models on our downstream tasks, but from there we had GPT-3, which is 175 billion parameters. It's been doing that self-supervised language modeling task on a massive internet scale text data set, and it seems to be able to do a ton of tasks just by prompting it. And so you just give it a couple examples of the task, and then it seems to be able to generalize to new inferences. And it's a pretty kind of mind-blowing idea that works so well without needing fine-tuning on the downstream tasks. And there's other interesting papers like the hypertext language model that shows how when you include the HTML tags, you get kind of additional structure in the prompting, and the way that the prompting is able to guide the model. Ideas like compositional generalization, Eric Zhang's recent article, Just Ask for Generalization. These ideas that there's so much compositionality present in language that you can just kind of prompt it to get whatever kind of performance or perform whatever kind of task you're after. So this kind of idea of restructuring the models and separating the retrieval and the reader, for one, it has this huge benefit of interpretability. You see what it's got in its input window to make its prediction. And then second, it's easy to change the information. If information becomes outdated or biased or it's just bad information, you can change it out and put in new information in this kind of separation of retrieval and reading with what the model is using to make these predictions. So then the kind of idea that if all you need is to have a general purpose model that can read over any retrieved information, that model should need less parameters because it doesn't need to store the information in its parameters. So hopefully that was a decent overview of the idea behind general purpose readers and a quick kind of timeline that's led us to thinking this kind of way and being really excited about retrieval augmented transformers, usually because transformers have kind of taken over as the thing that we're always using. So as a motivating example, here's the SQuAD Stanford question answering dataset. This is one of the most popular datasets used to benchmark natural language processing systems. So you can imagine two situations, one in which you receive this question, the atomic number of the periodic table for oxygen, and the model has to just generate the answer as 8, rather than having this retrieved context to kind of look at in the input window to reason about the information and then the question to produce the answer. So the idea of a general purpose reader would be that it's been trained on tons of these question and then context pairs such that it's really good at generalizing to a new question with new context. And that kind of approach, I think, has a lot of promise. So you imagine just having this extra information really facilitates the task of answering questions and all sorts of other kinds of downstream tasks, as we'll look at in the next slide, and see examples of systems where you can, if you add retrieval, you can improve the functionality of all kinds of things like classification or maybe even computer vision tasks like bounding box detection or semantic segmentation, image generation. If it has some examples in the input, it can help it further guide its prediction. And then you can kind of separate these two components, optimize them separately, and have different kinds of pipelines for flowing through this processing. I hope this image is big enough to clearly see the system. If not, this image is taken from CoSearch, COVID-19 Information Retrieval with Semantic Search, Question Answering, and Abstractive Summarization. And this image can be found in that paper, which is on arXiv. So here's this kind of system was really my, say, vector search moment, analogous to when people say their ImageNet moment in computer vision, or just kind of like the ImageNet moment, not like your personal ImageNet moment. But anyway, so this system was something that really inspired my interest in vector search and this idea of splitting out these components into retrieve and then read. So we start off with the document corpus, and this is built of the Cord-19. This is a collection of over 140,000 papers related to COVID-19, patient care, all sorts of relevant information. So from here, you do some kind of document index. And that's the cool thing that these vector search engines are doing, amongst other things, is they do things like they'll quantize the vector representations, they'll build up these kind of centroid graphs, and they make traversing this for nearest neighbor search, they turn it into an approximate search rather than exactly doing the dot product between your query and then 140,000, or as you imagine generalizing this to millions, or there are all sorts of problems where they look at massive amounts of vectors to compare to. So they build these indexes that really facilitate and speed up how quick you retrieve. So there's two kind of things. You might do the Siamese BERT, which is where you do that average pooling along the kind of like representation of each token to get a representation for the whole sentence. Or you do these sparse retrieval techniques like BM25, TF-IDF, where you have a sparse featureization of the documents. So this is term frequency, inverse document frequency. It's a way of like counting up how often the words appear relative to the whole set. That kind of idea of kind of like keyword-based retrieval compared to these dense representations. And you might have different applications for each of these two things. As I've been talking to people about vector search with the Weaviate podcast, you see there's all sorts of different ways of thinking about when people want a keyword search and when people want a neural search solely. And then Weaviate has this functionality to combine the neural and the symbolic search by using this kind of functionality. But to get back into this system, so once you retrieve the context, you're going to append it to things like the query. Like you could add context to the query and then use it to retrieve further. You can take these retrieved documents, append them to a re-ranking model, re-ranking recommendation, these kind of things, and you can flow it into question answering, abstracted summarization, a chatbot. You could say classify the query. There's all sorts of ways of flowing these pipelines so that you can supplement the downstream task with additional information through these retrieval pipelines. And then you have kind of at the end, this question answering model is like the reader that we're imagining. This would be like the general purpose reader has been trained on so many query context pairs that now it can reason really well over these new kinds of inputs. And maybe that reasoning has some kind of symbolic component to it as well, or maybe the symbolic component is just embedded in this part, but some way of reasoning over retrieved query context pairs. At the end of the video, I'm going to play a clip from my latest podcast interview with Malte, Pietsch, the CTO of DeepSet AI, the creators of the Haystack vector search engine. And they have these great pipelines for flowing through these components and plugging in these different kinds of ideas of query retriever, different kinds of readers like the retrieval augmented generation model, the RAG model, or different kinds of ways of flowing these pipelines. But this is kind of the high-level overview that I hope you take away from this video, is thinking about these kind of pipelines and what we might want to add in the middle of them, or different kinds of ideas of structuring these pipelines as we break up the task into retrieve and then read. So to come back to the motivating benefits of retrieve and read and splitting it up into, instead of compressing the whole task into a single neural network, splitting it into a retrieval, might not just be a single neural network. In the retrieval phase, it might be a whole kind of flowing system, but then say the reader is just a single neural network. The benefit I see is interpretability. For one, you see what it's retrieved, the context, and you can maybe that kind of attention map, as you see when people do attention map visualizations and they send the gradients back to the input. If the reader isn't that complicated, say it's like 2 or 3 layers, I don't know if that would work, but if it's not that bad, then the attention, that kind of visualization might be useful too, to see exactly what it's looking at in the input context, and you could probably trace the gradients that way, sort of like RadCam with these computer vision models. But anyways, the big idea being that you can see the context has been retrieved to make the prediction, and then it's easy to change out the information. And this is a pretty interesting topic where, say you're modeling Wikipedia data, and you ask it, who is the president, or these kind of things that change, who won the last NBA championship. This kind of idea of being able to change out the information, update it with the kind of the time information, would be easier with these kind of by separating out retrieval and then reading, compared to having a language model that's doing some kind of, say, continual learning, and you have those problems like catastrophic forgetting as you try to just update the information by just continuing looping through the training data with the new information. And then finally, the big sell that I think is that it avoids the need to store more information in the parameter. So the reader model doesn't need to store the data that it's going to be producing. So when it's asking you what's the atomic number of oxygen, it doesn't need to store that information in its parameters. It can just reason over what you've retrieved. And then I think that will avoid a lot of kind of the over-parameterization need of needing to store the data in the model. Here are some of the questions that I have about retrieve and read that I'm really excited to be exploring. The big one for me is the question around fine-tuning these models and where to fine-tune, how to do that, the power of these off-the-shelf components, and all that kind of idea. So before making the argument for fine tuning, the off-the-shelf components, like say a Siamese Burt retriever model, has been trained on like the MS Marco data set, or a massive collection of semantically similar labeled pairs, or maybe you could use data augmentation to form the two similar pairs, similar to how image representation learning has adopted contrastive self-supervised learning. But so that kind of retriever off the shelf combined with, say, a model that's been trained on that squad data set that we looked at earlier. And again, there are 200,000 of those examples of the atomic number of oxygen. There are 200,000 such examples in that data set. So you'd imagine that training on that might be all you need to generalize to any kind of problem. So combining those two off-the-shelf pipelines in something like Haystack that lets you easily pick the retriever, the reader, and then flow those pipelines, and you can connect to the Weaviate database to do the retrieval part as well. And then you could send it into the Haystack retrieval augmented generation model, or just a downstream task for processing the retrieved information. So maybe off the shelf will just work, and it probably will work for a lot of use cases. But then I think there are a lot of interesting things to think about if we are going to be fine tuning the model. So let's say we have a static snapshot of the retriever, and then we're going to fine tune our reading model. So say in the Keras bird example, we have the retrieval checkpoint of the Keras code examples, the Keras API reference, and the Keras developer guides. So we're retrieving that information to supplement new queries in the reader dataset. So maybe what we need is some kind of query paraphrase to avoid overfitting, like throw around some noise so it doesn't just overfit to the static retriever, kind of maybe a consistency-based loss where, say, the similar pairs are, say you retrieve, 1 to M documents and then 1 to K, you want to have a similar prediction as K plus 1 to M, and then negatives would be like randomly sampled documents for the context. Some kind of idea like having a contrastive loss to kind of force the attention on the retrieved information. So the next part is thinking about what multimodal retrieve then read is going to look like. As Weaviate has recently added the CLIP model, which is an image text contrastive alignment model, and thinking about adding all sorts of other kinds of data domains to these kinds of pipelines. We've seen things like the perceiver IO, pre-trained transformers, just kind of thinking that like this kind of transformer architecture should be suitable for all sorts of different data types. And then we've seen things like the text-to-text transfer transformer T5 that shows how kind of all these tasks can be formatted as language modeling and mapping the masked prediction into class labels and things like that. And then this really great article from Eric Zhang, Just Ask for Generalization. This really nails this idea on the head of the compositional generalization that is inherent in language, and the idea that if you can understand language, you understand generalization. And I think that's a really great analysis of this. And thinking about how language can kind of unite all these tasks is something that I see as being kind of like the interface for this pipeline. And just in general, say processing video is very heavy computationally. It's a massive input data type, as you have the height by width by RGB, and then you have the time sequence of say 30 frames per second. And then you probably want like 15 seconds of video at least. So it's a very computationally heavy kind of data domain. So maybe splitting this up and breaking down the different components can help facilitate just the overhead of doing tasks with videos, like video generation as maybe the most ambitious one, but just like video classification, all sorts of things. So finally, this is something that I've been working on for my PhD at Florida Atlantic University that I hope you'll find interesting as well. And so we've been looking at a data set of COVID-19 patient care and thinking about precision medicine and how vector search engines might be able to help us get towards this kind of future where you're not being treated with like a population heuristic, or even maybe it's more fine-grained than that, but you really have the similar patients and how the treatment plans for them worked out as you're guiding this kind of, as the doctors are making decisions about how to treat you given some kind of disease. So we've seen things like the decision transformer, as it shows how you can process, reinforcement learning tasks as sequence modeling through a sequence of reward, previous state action, timelines, and reinforcement learning is also a sequence-to-sequence learning problem similar to neural machine translation, longer text generation, say abstractive question answering, abstractive summarization. So we'd imagine that we can put all these same ideas apply to this kind of precision medicine paradigm of where you prepend examples of similar patients and their treatment trajectories, and say the physiological markers, the things that you record as you're kind of monitoring what happened with the treatment plan, and you can append these trajectories to the input sequence in the same kind of retrieve then read pipeline. And again, I think that if you train this reader model in all sorts of these retrieve and read kind of contexts, it could generalize to very interesting kind of cases in in precision medicine specific to medicine, I think there are all sorts of little subcategories of these diseases. And I think having the general purpose reader as trained in all sorts of different kind of maybe domains, like domain generalization, would be an interesting way to think about this kind of problem. So to wrap up the argument before concluding with a clip from my recent podcast with Malte Pietsch from Haystack, this is the OpenAI API, and I think it's just a great testimony to this idea of a general purpose kind of model. So GPT-3, it's able to just kind of do all these tasks given some kind of prompt, and people are able to just connect to the API and just connect to, say, artificial intelligence as an API interface through text descriptions of whatever the task is or the skill that you need the AI to perform. But I think kind of the idea of splitting this up into retrieval-based, plugging in the custom data set for your specific problem, and then using something like the Weave8 vector search engine to retrieve it, and then maybe using something like Haystack to further process it, or fine-tuning your models further, and getting this kind of customization to your particular task, and then also breaking up the parametric complexity of splitting it into retrieve and read components is something that I think will really kind of enhance this idea of general purpose modeling. The following is a clip from the Weave8 podcast. Please subscribe to Semi Technologies to check out future episodes of this podcast discussing all sorts of things around AI, deep learning, database systems, and particularly vector search engines. And yeah, for me, I'd say like my vector search ImageNet moment was when I first came across the co-search system from Salesforce Research. And this idea of the pipelines is the first time I really saw this diagram where you look at the document index, the retrieval pipelines going into different downstream applications like summarization, question answering, or say a chatbot. And this kind of idea of having these flowing systems, for me, co-search was my ImageNet realization when I first became really excited about these kinds of systems. So I'm really impressed as I was looking through the Haystack, how to use it and the different components of it. I really love the pipelines. And so before we get into the sort of the details of the kind of like the library design, I want to ask about more of your opinions on retrieval augmentation and kind of like retrieval transformers. And it's obviously very popular now with things like DeepMind's Retro and OpenAI's WebGPT, this really exciting idea of retrieval augmented transformers. And before I give you a chance to talk, I want to kind of quickly pitch this idea of, do you think that maybe the shape of, say, AGI or like a powerful AI, the next generation of that will be that you have such a powerful reasoning model that all you have to do is just plug in your data and then it can just retrieve it. And then this reasoning model will be able to adapt to any kind of data that you retrieve, such that the retrieval augmented pipeline is so strong that you don't really need as much fine tuning. And then from there, we can talk about the farm library and Haystack and all sorts of things as debate around retrieval augmentation and then the need for fine tuning.
Yeah, so I definitely see that retrieval augmented pipelines or models are like a super important piece towards maybe AGI at some point. And I mean, I think you can tackle it from two sides or two perspectives. One, let's say, just coming from plain transformer models. And if you talk about something like question answering, retrieval is just basically the way to speed things up, right? And to make it scale to millions of documents, having like some kind of filter before and really just seeing it that way. And that's how we, I think, initially kind of started it. Then I think with the, say, the rise of all these gigantic language models and more like generative approaches, it's really, I think, now about these two schools, two, say, mindsets, two beliefs, what is today actually helpful and where we'll end up in the future. I'm pretty sure that for today and the next years, I would place my bet on retrieval augmented pipelines, mainly for two reasons. One is basically interpretation. So if you, let's say, have something like GPT-3 or like from OpenAI, one of the models, and you ask the query a question and it gives you the answer, it's super hard to understand if that's correct or not. You don't know how it was generated, what kind of information is it based on. And that's a very powerful thing with retrieval and extractive methods, right? That you, with our users, often they get these results, but then they often also ask, where was that written? Like, give me the exact passage and what real data is that based on? And that's very easily possible. The second thing you already mentioned, like fine tuning or the way to adapt it to new data sets. If I have something like, I don't know, GPT-3 or another generative model, usually trained on a big public corpus from the internet. If that's your domain, perfect. But our customers are mainly like enterprise clients, maybe from aerospace domain, from some legal domain, from finance, some very deep tech stuff. And there are usually like words and meanings that are very different to general internet Wikipedia corpus. Yeah, I mean, these big models are not trained on it, so they don't work. And they get outdated very easily, right? If you ask one of the, let's say now 1-year-old models about Omicron or COVID or whatever, they won't know, and it's very hard to update. While with retrieval, it's just, hey, I index one new document today, and out of the box, my model knows or can find this information. So I think these are two powerful advantages. Still, like retrievers, dense retrievers, for example, there is, I think, some in many cases need for fine tuning and also like get a lot of boost if you fine tune for your domain. But it's then usually something you do once, and you can still like ingest new data and you're fine, and you don't need to retrain like every, I don't know, second day.